Well, I think I'm gonna start now, introducing us all together. So if somebody joins while I'm introducing, it's not that much of a problem. Welcome everybody to this nice afternoon together with Kevlin. Kevlin is maybe known because he knows 97 things about programming and Java programming. I bet he knows a lot more. He's just a pretty decent guy. So he will tell us today something about the architecture of uncertainty. Uh, I'm still not sure if he will be talking about sci-fi that he also writes or if it's gonna be some technical talk. Let's be thrilled about it. But before Kevlin starts, I kind of want to introduce us again to, well, show you who we are. We are the software engineering community of T-Systems MMS in Dresden. We are present since 2013, at first as an in-house team, and now we are trying to do a lot in our general community in the Dresden area or in online areas, as you notice today. Our goals are, in principle, exchange of knowledge, creation of networks between IT professionals, knowledge building, and also understanding of all the topics around software development and architecture. Besides, you see some people, some faces of us. I think most of them are also present today. So if you want to have a talk afterwards, we are always there for you. Speaking about we are always there, we have a lot of channels where we try to, well, further our goals. One of which you are in and now, that's the Seco Best Practice talks. We also got a hackathon in the second half of this year. I think the registration will start kind of in a few months. And we also have our big dev day this year again in a presence in the Messe Dresden. I think the registration for participants has opened today or yesterday already. So if you want to meet some people in presence, feel free to register there. We're also available on online platforms like our own homepage or our Meetup group. I think you know them. So that's it about us. Now I will hand over to Kevlin with his talk, The Architecture of Uncertainty.
Right, thank you very much for the introduction, Martin. Let me share my screen so we can check that that all works. Excellent. Right, so let's see. So hopefully you can now see that, and obviously my screen configuration has completely changed. So what I'm going to suggest is that what I'm going to I'll talk for about an hour on this topic, and then we've got plenty of time for questions and discussion after that. So yeah, let's start off. So that's what I look like when I'm standing up in front of people, and which I haven't had much opportunity to do the last couple of years, as I'm sure we're all aware. And my contact details, very easy to find me if you want to kind of follow up on any conversation or any topic, or link or just connect on LinkedIn. I have a very internet friendly name, an internet unique name. And my interest in architecture, I think architecture is an interesting thing because it goes back as an idea, it goes back a long way. I'll talk a little bit about that. But I also want to talk about this tension, this paradox that we have, that sometimes when people talk about architecture, they have an idea of things that are very heavily planned and decided in advance. And that's not really the whole story. And we often notice that comes into conflict and is in tension with the ways that we are increasingly working. And have been really. There's been a lot of shifts. There are always shifts each decade in software development. But what we've noticed is a general movement towards a more continuous approach. In fact, we put the word continuous almost everywhere these days. Continuous deployment, continuous. I kind of already started with continuous integration. These days, I found when I'm running workshops on things like test-driven development, one of the points that I make is that the biggest benefit is to do with continuous testing. When talking about the testing workflow. We see it in our tools, in other tools as well. Incremental compilation. If incremental compilation had been invented today, it would be called continuous compilation, but it was invented in a different era, so we use the term incremental. But all of this ties back to this idea that there is an interesting way of thinking about and reasoning about things, about how we're going to build things. So I co-authored these books a number of years ago with Frank Bushman and Doug Schmidt, and these are very much about patterns, design patterns, and the design patterns way of thinking. A lot of people, I still find that I talk a lot about the patterns way of thinking and what it taught me and what I learned from it. A lot these days, because a lot of people, I see it a lot. A lot of people don't really understand patterns. When you say patterns, they think, oh, right, you mean that book that was written by the Gang of Four in the 1990s, and then they reel off a short list of patterns to do with object-oriented design, and they think that these 23 patterns are patterns. The story turns out is a lot bigger and a lot more complex, and most people kind of miss that. But what is of most value is that inside this. Inside the patterns movement was an idea of how to think about development, an incremental feedback driven approach to architecture. Somehow that got lost, that message got lost, or rather it got reawakened. It is not a coincidence that when you look through the history of the patterns movement and you look through a history of the agile movement, you see a lot of the same names, and that's not a coincidence. It springs from the same source. It's the same idea. Just expressed from a different angle. So that's kind of my interest in that aspect. But ultimately, my interest is driven by code. As Martin mentioned, 97 Things Every Programmer Should Know, a book I edited just over a decade ago, and 97 Things Every Java Programmer Should Know, a book I edited with Trisha G. Kind of, first wave of lockdowns, we finished that book. Suddenly we had plenty of time to do it. And a lot of my interest is ultimately, it's always grounded in code, because code is where the software ultimately is. Everything else that we do, whether we have meetings, whether we draw diagrams, all of these are about kind of informing ourselves, learning something, communicating something. Ultimately, the reality comes down to the code. I ran a workshop this week for a company in Germany, as it happens, and one of the feedbacks from one of the organizers, because they were concerned, they sort of said, "Oh yeah, there's a lot of coding going on, and I wonder if we could do all of this with models." And it's kind of like the observation was, no, you can't, because ultimately what we're trying to do, specifically we were focusing on software craft, is you've got to produce the software. A diagram is a way of talking about something, but it is not the something. And that is a really important idea. A lot of people, when they talk about architecture, they forget that software architecture is supposed to be a practical discipline. It's not about avoiding building something. Because sometimes when we meet certain software architects, we think they're doing an awful lot of work to not build something. It's like they're avoiding the work. Software architecture is inherently practical. If you don't end up with a software system, then software architecture is of no use. Ultimately, software architecture is in the code. Don't let anybody tell you different. A building's architecture is in the bricks and it is in the steel. It's not in the drawings. That is the starting point of the conversation. But it's not the whole of it. Now, this leads us to an interesting idea, is that we've ended up with a kind of historical view where we have this idea, perhaps, that architecture is a thing that is fixed and planned in advance, which sounds kind of idealistic. And there's a reason that people like this idea. They like this idea because it means they don't have to deal with change. They don't have to deal with uncertainty. Or to put it another way, if we have everything planned, then there is no uncertainty. Yeah, we feel comfortable with that. Humans are incredibly comfortable with the idea of certainty. So I'm going to quote from one of my favorite authors, Neil Gaiman. He wrote, so the Sandman comics, you can get in graphic novel form from the late 80s through the 90s. These are absolute classics if you are into if you're into kind of like the more modern era of comics. These shaped a lot about how people think about comics. And there is a particular protagonist, a particular character. She's called Delirium, and she's kind of like always a little bit scatterbrained, we would say, delirious. And she says, "What's the name for things not being the same always? You know, I'm sure there is one, isn't there? There must be a word for it. The thing that lets you know time is happening. Is there a word?" And I love that way of looking at it. How do we know that time is happening? How do we know? What is it that we know that causes us to be aware of this? Her brother, who is someone of few words, says change. Oh, I was afraid of that. So we have this problem. We have this benefit, we have this problem. Is there are humans, there are two things that humans struggle with. One, things being the same all the time, and two, things not being the same all the time. Somewhere between these two extremes, the fact that we don't like change and that we want change, is most of what we do, most of what it means to develop software, most of what it means to be a human being. And the great Grace Hopper, she was a force of nature. She One of the people basically invented the idea of the modern programming language, the compiler. Mostly people remember her for being involved in the invention of COBOL. Now, I don't like the language COBOL, but what I do recognize is the work that she did in the 1950s and 60s on COBOL and COMTRAN, and advancing the state of knowledge of software development. She had a very clear way of looking at things, and she was unafraid to say that. So, as an observation, she sort of said humans are allergic to change. They love to say we've always done it this way. And when we look at software development, you'd think that in software development we'd be better at always wanting to talk about change because it's technology, and technology is in many people's minds associated with change. But I've kind of recently been looking at the way that we actually do develop. And I'm surprised at how little has changed. I'm surprised at actually how bad software development is at change. And more importantly, how bad we are at taking on knowledge and solving problems. I'll probably come back to that a little bit later. Interesting enough, it ties in with my view on patterns as well. So Grace Hopper said, "That's why I have a clock on my wall that runs counterclockwise." Now, I was inspired by this quote a few years ago, and I thought, I live in the internet age. Surely I should be able to find such a clock. That's my clock. I have this clock because Grace Hopper had this clock. You can go online and find a clock that goes backwards. It kind of messes with members of my family when they come into my office. They go, "What's the time?" They look up, and it's just like, "Okay, I won't ask." But that's the point. We are breaking with a convention here. We're surprising people. And what we need to understand is change is normal. And this conflicts with our traditional view of what we mean by architecture. And I want to talk about this idea of certainty, and I want to talk about this idea of rate of change. So let's get to Paris. It's a beautiful city. And I'm going to use that as the backdrop for quoting Martin Fowler. Now, Martin Fowler had this observation that has changed a little bit over the last few years, but is still mostly true. He said architecture is a term that lots of people try to define with little agreement. There are two common elements. Now, I would say actually these days we have slightly more agreement on the term architecture than we did perhaps 20 years ago, nearly 20 years ago when he first wrote this. But what he says is still very much the truth. One is the highest level breakdown of a system into its parts. Some people think of architecture like this. Other way of looking at it is that decisions that are hard to change. Now, one of the things that I want to observe here is take a step back for a moment. Software architecture is one of those concepts and one of those terms, if you like, that that has a. I think somebody's got the. By the way, I think somebody's got their mic open. I think it might be Stefan. Just judging by what I'm seeing here. There is an interesting idea. Why do we not have one fixed definition of architecture? We have a lot of very clear definitions. If I say, okay, I'm going to develop an object-oriented application, I'm going to use an object-oriented language, we have a fairly clear idea of what we mean by object orientation. And likewise, if I say I'm going to do something in a functional way, we have a clear idea of that. If I talk about using a relational database, there's no ambiguity about what I mean by relational and database. These are very clear terms. So how is it that we've ended up with a term like software architecture and people can't agree on it? Part of the reason for this is that this term comes to us not from one source. In other words, some terminology comes to us from one place, and we can see its evolution, we can see its point of inception, and we can see how it evolves. And maybe it evolves away from its original term, that's quite possible, but there are certain terms we can see where they came from, and we can see their point of origin. So for example, patterns, that's actually quite easy. That comes from the world of building architecture and the late architect Christopher Alexander. It's very clear he introduced that term. We borrowed it into software development, and it's evolved since. We can pick on the term agile development, for example. Again, that has a clear point of origin and a clear group of people that it came from. Most of what people do these days and call agile is definitely not agile. But that's a separate discussion. But we can still chart the history of it. It's very clear what it how it's come to us. But the term architecture, until relatively recently, I was not entirely sure what we had, where the term came from, or when the term started being used. And I sort of had it in my head that 1970s was probably the right period of time. People like Frederick Brooks, who wrote The Mythical Man Month, used the term, although to mean something a little different to the way we might use it now. People were using it in the 1980s, and there are a number of cases where I see the term architecture being used. What I find interesting is that recently I dug through something and I found a publication from 1969 with a half-page definition of architecture. So actually the term architecture goes right back to the 1960s, but it comes from many different places. It's a metaphor that we find useful. Whenever we see structure, we go, oh yeah, it's got some kind of way of talking about the structure, and we use the term architecture. We see it in other disciplines as well. We see it in terms of biology. I've seen it in terms of book writing. People talk about the architecture of a book. So this is a term that gets used as a metaphor by many people. But what do we mean when we say software architecture? How do we avoid the problem that we have a conversation and one person says architecture, another person says architecture, and actually we're having two different conversations? We're using the same words, but we actually mean something different. So it's worth having a little bit of a handshake to agree what is it that we are talking about. And this idea, the highest level breakdown of a system into its parts, is one of the attractive ones that people do. And you tend to see this on PowerPoint architecture, or sometimes gets called PowerPoint architecture or architecture. I'm not very keen on this view because the high level view, it seems to suggest that the detail doesn't matter. It seems to suggest that only the big box view of a system is important. And if you spent any time doing software development, you will understand that although that is a valid way of looking at a software architecture, that is not necessarily where all the cost lies. In fact, the way that I now put it to people is if somebody puts up a diagram and says, this is the architecture, the one thing you can be sure of is that that statement is false. That is not the architecture. The one thing you doesn't mean you know what the architecture is, but when they show you a diagram, that is not the architecture. What it is a view on the architecture. And that is a very different idea. Something that is complex can have many different points of view. To understand the whole of it requires multiple points of view. To have just a big breakdown of the boxes is likely to ignore where all the action is and where all the interesting design decisions are. So for me, I don't find the big breakdown, the big box view of architecture. I'm not saying it's not helpful. I just don't think that that is architecture. If you think that that is architecture, you are immediately closing off most of the stuff that is going to surprise you. Unfortunately, many decisions are made in terms of the big boxes. You know, people draw, here's this technology, they'll draw a line between it. They won't talk about the semantics of the relationship, and they will do all of their costing and estimation just based on that view alone. So for me, a more valid one is this idea of decisions that are hard to change. And the definition from Grady Booch, I think, is really quite helpful here. Architecture represents the significant design decisions that shape a system, where significant is measured by cost of change. So actually, I'm going to do something a little bit different here. I'm going to add in a blank slide. Just move a few things around my screen. Can just get those all sorted. And I will show you, there we go. So hopefully what you see is a blank screen. What I want to do is I want to pick up that definition that Grady Booch gave us. Architecture represents the significant design decisions that shape a system. So the first thing to observe there, what he's saying is...
We're still seeing your presentation.
You're still seeing the presentation. Okay. So in that case, wait, in which case you will see something change in a moment. You will see something change in a moment. So what I'm learning here is that WebEx does exactly what Zoom does, which is when a black screen is shown, it doesn't transmit the image.
Yeah, no, because it's black, yeah.
It's black?
Yeah.
Okay, good. In which case that is exactly what we want. Right. Okay, so I'm going to just draw. Now you should see a squiggly line.
Yep.
Yeah, there we go. Okay. I'm going to say basically everything within the squiggly line we consider to be design. Everything within this squiggly line we consider to be architecture. Now, in fact, let me diagram that a little more consistently. So in other words, what Grady Booch is saying is that the idea is that architecture represents significant design decisions that shape a system where significant is measured by cost of change. Not all design decisions are significant. Okay, that's what we're saying here. We are basically saying that significant with respect to cost or effort of change. These are the things that are harder to change. Now, the reason I've drawn these as squiggly lines is because there's no hard boundary. There's no kind of sense of like, you are now leaving the architecture sector and now entering the regular design sector. That's not how it works. It's a soft boundary. It's an approximate boundary. But what we are describing is the idea all architecture is a subset of design. Therefore, architecture is design-based. But what we're left is the challenge of how, first of all, how do we know that something is architectural or not? And we're talking about it in terms of scale, but the scale is not how big it is on a diagram. The scale is not to do with the size of the box. It is to do with the amount of effort it takes to move the box, if you like, or to change something. This also tells us that we are not going to be able to find out everything that we need to know in advance, because we don't know what are the things that we're going to need to move. And let me just clarify, given this, what one of the considerations that we want to make. Let me talk about this idea of the boxes. Let me talk about, imagine we have some kind of component there. Imagine we have another component over here. And as you can tell, the size of the components is clearly quite different. And that if we were to take, if somebody were to say, oh yes, well, the amount of we need to change something here versus changing something here, clearly the big box makes it look like there's going to be more work in the big box. But this is to ignore what architecture actually is. Architecture is mostly about relationships. It's not about really about the things. It's about the relationships between the things. And what do I mean by that? Well, let's go and draw some other things. So here I am going to draw a lot of dependencies on the smaller box. Whatever that box represents, whether it represents a component, an interface, an API, or even just a simple design decision. So here what we're seeing is a lot of dependency is inward bound. Over here, I'll keep things simple. Our initial view is that the thing on the left, when we look at it like this, we think of it as being the simpler, smaller thing. The thing on the right looks bigger and more complex, and that's the normal way it's presented in a PowerPoint architecture. But what we normally don't do is we don't normally draw the users on. This is actually something that I tend to do diagrammatically whenever I sketch things, is what is using this component? We're considering the component in isolation. What is using it? The other thing that I tend to do is I tend to draw people on, because we always forget that people do the work. People are associated with code. When we say this component is expensive to change, what we're actually making is a statement about people. We're not actually making a statement about the component. Economics is a social science. So in other words, who are the people that are affected? Now, when you look at it like this, it is incredibly obvious that although the thing on the left is small, if I say I'm going to make a change here, clearly that change is going to have more significance than the change over here. In fact, if we have no users, by the way, this is a good piece of advice for dead code. You can have a large amount of code. Oh, what's the cost of change? Who's using it? Nobody. The cost of change is zero. Okay, we're not very good at getting rid of dead code. But the funny thing that we are defeated by, the thing that is subtle, is this one. Okay, so that could be an API, that could be an interface. How easy is it to change an interface? Well, the more people you publish it to, the harder it is. And in fact, we can actually even draw out a kind of a zone model. Sometimes I talk about this in terms of organizational distance. Okay, let's just say that this is my team. Let's just say that these are other teams within the same organization. Let's say that these are teams outside our organization. The further away you go, the greater your organizational distance, the harder it is to make a change. And that's quite an interesting one, because it's nothing to do with the size of the thing. It's to do with the size of the dependency set. That's the bit that we miss. Architecture is not really about the boxes. It's about the size of the dependency set on the boxes. That is where the cost lies. That is where the difficulty lies. You see this in any API that's been around for a long time. You also see it is embodied in terms of mistakes. So let me just show you a very simple example. Let's look at the Java doc for Clonnable. Let me just pick on some reason that is not. Okay. Okay. So I'm picking on that. I'm also going to pick on, let's see, the .NET clonable definition. I'm also going to experience a slow network, which is a little bit annoying. No, my network seems to be fine, so I'm not quite sure what's going on there. That must be Microsoft. So here we go. We've got Clonnable there. And then I'm going to go to Wiktionary. Now, the reason I'm doing this is I want you to notice this, the spelling there. So that's in .NET, iClonable, spelled like that. Then I'm going to go to Java, Clonable, spelled like that. Then I'm going to go to Wiktionary, and I'm going to show you how to spell Clonnable. Now, as you're aware, English spelling is a complete nightmare. A lot of people say, English does not have a logical system of spelling. Unfortunately, they are wrong. English has about 6 or 7 logical systems of spelling. That's its problem. If it had one, that would be easy. It has about 6 or 7. But this is, if there is a standard way to spell Clonnable, it is this. You will notice that there is an extra E missing. But notice down here, alternative forms, especially in computing contexts, Clonnable with an E. A spelling mistake back in the mid-1990s led to Java popularizing this spelling. Microsoft, a few years later, then adopted the same spelling and put an I on the front of it. Now, I want to ask you a very simple question, because this is a really interesting one. Is spelling of an interface, is the spelling architectural? Normally we think, oh, spelling, that's just a small detail. That doesn't matter. That's just naming. Okay, tell me how much it would cost for Microsoft to change the spelling. Tell me how much it would cost for Oracle to change the spelling. It's like, right, now I understand. It does cost a lot. Think about it. You may be familiar with other popular spelling mistakes. HTTP referrer is incorrectly spelled. That's part of a protocol. If they change that, if they correct the spelling of that, the web will break. So the other definition we can use for architecture is, if I make this change, how many people will shout at me? The more people that shout at me, the more architectural that was. And this is not just a point about naming. What I'm trying to say is that the value of the name, or the weight of the name, is related to the number of people that depend on it. This is why renaming a local variable is not architectural. This is why renaming a class that is only used within your team when you have automated refactoring tools is not architectural. But the minute I publish that to somebody else and I don't control their code, suddenly we've entered a different realm. We've crossed a boundary. So architecture is not about the bigness of the things. It is about the bigness of the relationship to the things. The more relationships we have to the things, the harder it is to move. So this gives us a very different view of architecture, and one I find much more useful. It feels more realistic. However, it does leave us with a problem that Ralph Johnson highlighted. Architecture is the decisions you wish you could get right early in a project, but you are not necessarily more likely to get them right than any other. In other words, if you have a time machine and you went back and told yourself, hey, you need to pay attention to this, you would probably get some things right. You would also miss other things that were important. The idea is, how difficult is it to change certain things? Now, this has a number of implications. A lot of people, for example, do not think, oh, well, the platform or the programming language. I often have people telling me, oh, yeah, we've got a code base and our code base is in C++, or we've got a code base and our code base is in Java. Okay, so so Java is part of your architecture, or C++ is part of your architecture. And they go, oh no, it's not part of our architecture. It's just an implementation detail. Okay, so that means you should be able to change it easily. And then they kind of look at me and it's just like, well, no, because we've got a million lines of this stuff. We can't just change it. In which case it's part of your architecture. It's like, it's kind of the foundation you've built on it. It's almost invisible. There are a number of practices that we have that are almost invisible. So this idea of architecture is anything that is going to be difficult to change is part of your architectural set. If you are working with a different architecture where you do have multiple languages and the languages are isolated from each other, so for example, microservices or any other process-based architecture, then the language is not as architectural, but your inter-process protocols are more architectural, because those are the things that you can't change. If you change those, they will take time and effort to get right. So here's the challenge. We're not going to be able to predict the future, and yet we want to. So what do? Well, we have a very conventional historical view. We do a lot of thinking up front. Okay. The name we ended up giving this in software development is analysis. Then we talked about, okay, now we're going to make all the big decisions. We're going to call that design. And that's where our architecture comes from. And then we're going to code it up and then we're going to test it. Now, this all looks beautiful on paper. It's a very simple explanation. It's very rational in one sense. The problem is that we are going to be surprised because most of the reality, most of the feedback happens later on. So we spend a bit more time. We think, you know what, we should have spent more time thinking at the beginning. And we spend more time thinking at the beginning. There's a great irony to this. The idea of spending more time in the thinking phases, let's think about what the problem is, let's think about how we're going to build it, reduces the amount of time that we have to actually find out if we were right. This approach, so this is the great irony. When people, having been involved in software development for a long time, I've kind of seen iterative and incremental development rise in many, many forms. And there's always this idea, oh, we should just do everything right, as if sitting down and not developing software. So let me just clarify. This is the part where we're not actually finding out whether or not our stuff works. We're doing it in our heads. And one of the great things about doing things in your head is that things never crash. And integration is easy in your head. Honestly, I can just imagine two different pieces of software and integrate them instantaneously in my head. To do it in the real world requires effort, and that's where the resistance is. That's where the surprises are. That is where our assumptions are, and many of the things that are not easily moved. This is why we've encouraged people, kind of since the 1960s, to work in a style that is more interwoven, more interleaved. Because this approach is very high risk. The idea that you do your architecture up front is a massively high risk approach. And what is ironic is that this approach increases the risk. It basically means your risk point is here, because you keep pushing it back. This is the point at which you actually get feedback on whether or not your ideas are good. Now, clearly we have to make some decisions early, but there is another idea here as well. We need to accept that we are operating with incomplete knowledge. We are always operating with incomplete knowledge. Therefore, how would you work if you did not know everything? And that's quite an important idea. How would you work if you did not know everything and could not find out everything until you had delivered, or until version 10? Okay, how would you work if that were the case? Not how would you work if you did know everything. I think we've all got a reasonably good idea of what that looks like. So this quote from about 30 years ago from Edward Berard, he tended to talk about recursive development. He regarded this idea of big to small in a very deep way. But it's a lovely observation. Walking on water and developing software from a specification are easy if both are frozen. So I'm going to go back to a book that everybody ignores, although it seems that Scrum is one of the most popular agile approaches in the industry. Most people doing Scrum have either never heard of this book, but certainly never read it. It's kind of interesting because it'll give you a very different view of what Scrum is to what the view that people get now. I'm very much in favor of the kind of 1990s and early 2000s Scrum. The stuff that is people push now, I'm not so keen on. I don't think that really is Scrum. It's a good way to make money if you're a certified Scrum Master, though. But there's a lot of really good ideas in here. Just simply looking at how to think about development. One of the observations that Ken Schwaber made is he distinguished between different approaches to creation of things, process models. And he's talked about this idea, the defined process control model. Okay, he distinguished between different development processes and just contrasted two, defined and empirical. Defined process control model requires every piece of work be completely understood. Given a well-defined set of inputs, the same outputs are generated every time. That doesn't really sound like software development to me. I mean, it's just like every piece of work be completely understood. Actually, let me go back on that. It does sound like software, but it doesn't sound like the bit that people normally talk about. What we've just described there, given a well-defined set of inputs, the same outputs are generated every time. I know what that is. I have a name for that. It's called a function. And I've seen things that look like this. They're called compilers. You give them the source code and then they produce the same software every time. Compilers were invented in the 1950s by people like Grace Hopper and John Backus. What they did is they basically created a formal notation for expressing things that were not at the machine level. And when you use that formal notation, it would generate the required code. And you Give it the same formal notation, it generates the same formal code each time. It's amazing. So in other words, this is an interesting thing, because what it means is that in software development, we have solved a problem that many other disciplines still have. We have solved the problem of manufacture. What do I mean by that? Let me see if I can find examples around my desk. I've got a pen here. Do I have another pen? Yes. Awesome. Right. I'm quite fond of these. These are Pilot G2 pens. I've got two here. They are effectively identical. In fact, I have about 10 more on the other side of my office. I keep regularly ordering these. These are, to all intents and purposes, identical. What I'm describing here is the manufacturing problem. The purpose of manufacturing is to create multiple artifacts that are identical. The purpose of manufacturing is to eliminate variation. In software development, we've solved that. It's called the compiler. It's called the build system. We solved that a long time ago. And you know what's happened over the last few decades is we have got better and better at solving certain classes of problems. So, these days we are much more used to the idea that a team has continuous integration. I mean, not every team. I was having a conversation with a friend, Toma, just a few months ago, and he was horrified by a team that he had just recently visited. That they still had one guy. They had the integration guy. This used to be a relatively common role in teams. When we talked about integration, there was a person and they had the knowledge. It was like a dark art. And it's just like, okay, give it to the integrator. And gosh, okay, but don't disturb him. Just feed him pizza for the next few hours. Don't disturb him. He's going to integrate everything. He's going to deal with the problems. A lot of teams still had this role. Now, I was very fortunate. The first large company I worked at, we had a nightly build. And we always did nightly builds. And these days, nightly builds seem kind of quaint. But this is like 30 years ago. Having a nightly build was quite cool. The only other people that did that were people like Microsoft. We had a nightly build. And that automatically meant that every single morning we knew exactly the state of our system. And we've only got better. We've become more continuous. We have created build systems that take a well-defined set of inputs and they generate the same output every time. In software development, we have solved the problem of manufacture. We create identical artifacts all the time. The challenge of software development is therefore not to create identical artifacts, it's to create artifacts that are different. The value of software is not eliminating variation, but it's producing it. Because if you think about it, what is the nature of your work? In software development, you do not produce the same thing again. You do not repeat your work. You produce different work. Therefore, you don't know what you're doing, because if you already knew what you were doing, then you've done it. If somebody says, that piece of code you were working on last week, yeah, well, I'd like that. And you sit there and go, well, I'm going to have to rewrite it. No, you just refer people, oh, it's here in the repository. What about the version you had a month ago? Oh, let me just roll back time, because we have time machines, version control systems. I roll back time. I can produce and pull out anything that we've ever worked on. If somebody says, the system we deployed last year, I need to see that, you can do that. And that's not a problem. If somebody says, what we need to do is develop the thing you've already developed in exactly the same way, that's a solved problem. You don't have to do anything. It's not like going to a restaurant. If you go to a restaurant and you say, I'd like what they're eating, the kitchen has to go away and reproduce it. We don't have that problem in software. The problem that we have is that somebody comes along and says, I want that, but different. That system we did, and we did that in C++, but we want to do it in Java now. That's not the same system. You're not rewriting the same system. Although we say rewriting the same system, it's not. It's completely different. It's made of different stuff. Okay? It's actually constructed using a completely different programming model, a completely different technology platform. The idea is that it has similar functionality and it serves the same role, but you're not actually writing the same system, because if it were the same, then you just give people the source code you already had. What people are asking for is difference. We want that, but different. When people ask you for something, oh, our competitor has now got this feature, we need to add it to our product. We want the same product that we have, but different. When somebody asks you to add a feature, they're asking for a difference. When somebody asks you for a bug fix, they are asking for a difference. In other words, the whole point of software development is that we produce differences. We don't produce the same things, we produce differences. By definition, because they are different, it means we don't know everything about them. So therefore, we do not have complete knowledge until we have built it. We need to have a different approach. So defined is not going to cut it. The empirical process control model, on the other hand, expects the unexpected. Very Monty Python kind of sounding thing. It provides and exercises control through frequent inspection and adaptation for processes that are imperfectly defined. The idea is you're supposed to change your process as you are going through it. You don't set out to have a fixed process. You set out, it's a process of inquiry. You set out with incomplete knowledge about what you're going to build and how you're going to build it. Now, that doesn't mean you don't know anything. You normally have a very good starting point. And the more experience you have, and the more you're prepared to listen to your experience and the experience of others, the better your starting point. But that still doesn't mean you know the future. And then we have this interesting clause at the end. These processes are imperfectly defined and generate unpredictable and unrepeatable results. Now, for many people, particularly project managers, this sounds like a very scary sentence. Why would you want something that was unpredictable and unrepeatable? We want repeatability. I tend to go against this. We don't want repeatability. The first time you do anything, you probably do it slowly and with a lot of mistakes. The second time you do something similar, you do it faster and with fewer mistakes. You avoid many of the mistakes that you you had the first time around. In other words, you take advantage of your experience and the experience of others. You see, that's one of the reasons I got into patterns originally, is patterns are not about drawing boxes and just giving names. They're actually about trying to capitalize on other people's experience. The whole point of a pattern is it's somebody else's experience, and you're able to use that to move you further forward. But this also gives us a very different style of development. Style of development that tells us that with all of these activities need to coexist, that our architecture, we make decisions early, but we also make decisions late. We don't have to make all of the decisions early. We're allowed to change some of them. We will get some of them wrong, and some of them will be hard to change, but we don't need to do all of them up front. But more importantly, this tells us, in fact, what you're seeing on the screen is one of those comfortable illusions. And what I mean by comfortable illusion is I've fallen into the trap of doing PowerPoint. Everything is lined up. The real reason that we break things down is so that we can change our mind. The whole point of doing it is because we are working with incomplete knowledge. And as our knowledge grows, we start going, oh, actually, we don't want to do this. We want to do it this way. So Nassim Taleb, perhaps better known for his book Anti-Fragile. His first book was Fooled by Randomness. And he made this observation. He says, people overvalue their knowledge and underestimate the probability of their being wrong. This is important because what I've said is we are always working with incomplete knowledge, and we're not very good at detecting our own lack of knowledge. Yeah. If you have a product owner telling you a whole set of requirements and they tell you, oh yeah, in 3 months' time, we're going to need this, in 6 months' time, the one thing you can be sure of is they're wrong. There's a very, very high probability that what they are saying is not correct. But if you tell them this, they're going to be very upset at you. They're going to say, well, hang on, no, I know what I'm doing. You're just a software developer. The problem is that you are actually right. It's just not it's not good people skills to tell people that they're wrong. They don't know that they're wrong because they're human. The same way that we don't know we're wrong. It's why we make software too complex sometimes, because we think, oh, I know what the future is, so I'll add this feature now. And what we've actually done is we've added a guess. And now we've got to maintain that guess. And that guess is probably wrong. And when we actually do need the feature that we described by that guess, we'll discover it looks different. But we still have code that looks wrong, and we've now got to deal with that. We've created a maintenance headache for ourselves. We didn't solve the problem in the future. We actually created the problem in the future. We are not very good at evaluating our own level of knowledge. When we don't know something, we often don't say, you know what, I'm not sure. We say, oh, I'm pretty confident. So what we need is a better framework of understanding. Philip Armour came up with this kind of framework, the 5 orders of ignorance, which I find very useful in the context of software development. And as things should be in software, it starts at 0. 5 orders of ignorance. Level 0. What is level 0? Level 0 is a lack of ignorance. It's the things that I know that I know. Okay. I know, for example, I know that I speak English. Okay. I know that I can speak English. I know I can write English. It does not surprise me. Lack of knowledge. I know what I don't know. In other words, you're not surprised. So, for example, I know that I don't know much German, for example. I mean, I have what I refer to as Speisekartendeutsch. Okay, I can, I can order off a menu. I can read street signs. I know when my flight has been cancelled, when my train is delayed. I can interact in a hotel. I can get myself a meal. I can get myself fed. I can't hold a deep conversation, and that's something I know that I don't know. Okay, in other words, it's something I already know that I don't have. As you can tell from the spacing on the screen, and although we've got 0 and 1, which are the fundamental numbers of computing, there's more. The problem that we have is even with just these two levels, I want you to think about how you estimate work, but also importantly, how you estimate when we talk about architecture and decisions. When somebody says, how should we structure this API? Should we use this method or this method? How should I partition this particular interface? Should this method take a set of options as an extra parameter or not? At that point, we're already dealing with things that we don't know. How good are we at acknowledging that? And how do we know how much effort it's going to take? There are the things that we know. There are the things that we know that we don't know. Then there are the things that we don't know we don't know. This is where it gets fun, because we don't know how to estimate these, and we are surprised by them every time. This is where assumptions live. An assumption is something that you believe, but you don't know that you believe. Normally, we only discover assumptions when they are contradicted. In other words, somebody tells you something, and you said, "Oh, I'd assumed that everything was going to be a 32-bit minimum addressing, and I actually had that for a system, that it was going to be, it was a standard address." And it's like, no, that's not true. Right. Okay. So therefore, everything that I've had this assumption, but I was wrong. You've had this belief, but you only discovered the assumption when it was contradicted. You didn't know what you didn't know. How do we account for these? But more importantly, lack of process. These are the things that are unknowable. We have no way of finding these things out until we find them out. We have no process for doing that. So, for example, we have no way of estimating those. So, for example, how many people do you think in 2019, how many people had for their plans for 2020, global pandemic disrupt everything that we do, including the work of our customers, the work of our developers, and everything? How many people had that in their plan? Nobody. And how would you have found that out? Because you see, the interesting thing is, lack of awareness is something I can deal with. I know that I have assumptions, I just don't know what they are. Well, how do you find your assumptions sooner? Start building. Okay? Yeah, but we don't know what the architecture should be. I've got some ideas. Let's start building it now. We'll get feedback. In other words, what we'll discover is when we're wrong. We'll discover it sooner. If we start, the sooner we start, the sooner we discover. We become aware. But there is no process that will accelerate time. Lack of process. We genuinely don't know. And these are the things that really, really surprise us. And then there is level 4, meta-ignorance. Actually, Philip Armour describes this as you don't know the 5 orders of ignorance, but now we do. So that solves that. Another way of looking at this is to classify our knowledge into these: the known knowns, the known unknowns, the unknown unknowns, the unknowable unknowns. Unknowable unknowns are things like, you may have come across this phrase. Sometimes people use it when they're talking about Scrum and Agile approaches. They say you should prioritize your requirements by business value. There's only one problem: you can't. It's not possible because you don't know the business value. Yeah, you don't know the business value of a feature until it's actually been built, released, and used. At that point, you can make an assessment of the business value, but you can't prioritize in the past based on something in the future. Okay, so prioritizing by business value is not actually possible. You can prioritize by estimated business value, but that's not the same thing. So business value future business value is an unknowable unknown. You won't know it until it arrives. Most of architecture is in this space, some of it is in this space. But what we're dealing with here is a recognition, referring back to Grace Hopper, an acknowledgement that the most important thing about what an architecture is, it's an embodiment of knowledge. It's an organization of knowledge. It's the organization, if you like. As she says, to me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. She's kind of basically saying that software development is effectively applied philosophy, which I think is quite a cool thing. I mean, that's a lot cooler to have on your business card, if we still have business cards, on your business card than software developer. Applied philosopher, So, but what she's actually saying here is quite important, because what it tells us is that an architecture is an organization of knowledge. Effectively, every software system is an executable Wikipedia. It is, here are the things that we know, and these relate to the problem domain, they relate to the technical domain. Here are the things that we know and collectively have decided about how we are going to build this system. We choose our paradigms and our programming languages and our libraries to express these various ideas. A paradigm or an architectural style is a choice of what we believe to be important in this world. Do we consider processes to be more important, or the most important idea? Or do we have a data-centric view? Is data the way that we view the world? Each paradigm has a lens through which it views concepts, and you organize your structure. It's a little bit like, how do you organize a library? Okay, there are lots of different ways of organizing libraries. I'm actually looking at my bookshelf at the moment, which I reorganized last year. That was a big mistake. I still can't find everything. But some people will organize their books according to just the author, or they will mix organization according to the theme. So actually, I can see from where I'm sitting, I've got a row of books on patterns. It's not a perfectly aligned row of books, but the next row of books is mostly on agile-y type stuff. And then the next one down is kind of software craft into computer science kind of stuff. And if I look to the other side of my office, I've got a row of C++, I've got a row of Java, in other words, that's how I've chosen to organize it. That's the paradigm of organization. If I change that, then I would have the same books, the same knowledge, but I would structure it differently. The relationships would be different. So this is what you're doing when you are coding, when you are making broader decisions about the component arrangement of your system, the layering in your system. You are making choices about how to organize your knowledge, and that knowledge is executable. But the point is, where does learning come from? Learning comes from finishing things. Okay, that's what you learn from. So that's why we need to be very cautious with the idea of having big kind of project end goals, but also an idea of, like, we do the architecture at the beginning, we deliver the project to the end. Actually, what we need to recognize, to borrow a quote from Tom Gill, which I recognize is not in my talk, a bit of a mistake, architecture is a hypothesis. That's the way we need to view it, because we don't know everything that we need to know in order to make the right decisions. So we need to have this kind of feedback cycle. Now, when it comes to feedback cycles, there is the simplest way of looking at how to generate a good architecture is that we do plan it. So let's be very clear, I'm not against plans. We do plan it, and then we do it, and then we study it, and then we act on what we just learned, and then we do it again. We keep on going. The point here is that historically, the way that many projects have approached is they've basically done it this way. We do a lot of planning, then we do a lot of doing, and then we're done. What we're saying here is, do a lot of planning, do a lot of doing, look at what we've got, then act on it. You have to do both of these bits, by the way. I've seen teams, it's really hard to do this, do the thing that generates the things that you're going to observe. Now you observe them and reason about them. Why is this happening? Why is it that we're always struggling with these changes? Why is it that we seem to have to keep changing and evolving our APIs? Why is it that we always have integration problems? Why is it that this particular subsystem we always seem to lose time in? It's a legacy system. Why do we always get our estimates so incredibly wrong about the work that's involved on that? Why is it harder than it should be? This is where we raise the questions and put forward new ideas about what to do about them. And not all ideas are going to work. And we feed that back in and we repeat. So what I've done here, in fact, I was wrong. I do include the Tom Gill quote. But what I've done here is I've tried to show you that architecture, we don't know everything that we need to know to take all the big decisions in advance. And by definition, some of the things that we need to know are in the future. That means that we will be wrong. So the first thing you have to accept is you will never know everything that you need to know. Two, that means that some of the decisions you will take will be wrong. By definition, the probability that you'll get everything right is incredibly low. And if you do find that you made every decision correctly, you're probably missing something. you probably missed the ones that you go wrong. You need to kind of view that it's an empirical process. That's the other thing about the PDSA cycle, the Deming-Shewhart cycle, is it's an empirical process. It's a constant process of theorize, experiment, which is why I like the Guild quote here, which I did include. Good, I was glad. I thought I included it. I was putting the slides together. Architecture is a hypothesis that needs to be proven by implementation and measurement. What he's saying is it's not a fixed artifact. You adjust your hypothesis. It's a kind of belief system that is testable. So we prove it, not in a mathematical sense, we prove it in the sense of testing it by building it and then measuring it. But let me be very clear about what we're saying when we measure stuff. When we say measure, I am not just talking about, this is not just about performance. Often people look at this and think, oh, okay, we're talking about performance. Yeah, I can see that. We got maybe two different ways, two ideas come from the team about how to improve the performance of something. So we build a couple of prototypes, or we make a couple of, we fork and make a couple of changes, and then make a couple of other changes, and then we run performance tests and we see which one works better, and therefore we measure it. Absolutely. But that's not the only kind of measurement. I want you to think about all the other statements that people make when they talk about their architecture. Sometimes they will make statements like, oh, let's separate this into a core and extensions. And therefore, we'll have an API between these. Therefore, this will make the code more extensible. Why are we making it more extensible? Because it will make it easier for the developers in future. Because now when they have to add these new requirements, they just plug in. That sounds like a really good idea. But is it a good idea? Well, I don't know, because I don't live in the future. I mean, it sounds like a great idea. So what we do is very much the kind of the Morpheus matrix kind of thing. Show me. You got to build it, implement it. And then what does measurement mean? Measurement means that in 3 months' time, we put a date in the calendar. 3 months' time, we have a review. 6 months' time, we have a review. 12 months' time. In other words, we keep coming back to our past decisions. We keep coming back and saying, why did we take this decision? We took this decision because it was going to make the code easier to work with. Okay, 3 months in, is that true? And maybe it is. And somebody might say, yeah, absolutely. It really simplified the work that I was doing. A company I worked at years ago, very much a more procedural, classic, old school C kind of place. They decided to build a set of libraries for something because they thought it would make something easier. And then they had a new system they had to build. And one of the developers, a colleague of mine, Patrick, who, lovely guy, but not necessarily the best developer, when he came to build the new system, he said, oh my goodness, that was incredibly easy. I just had to, it was like putting Lego bricks together. He said it saved so much time. Therefore, there's our measurement. What is the developer experience? Yeah, this took less time than we expected and it was easier to do. Well done us. We built it right. On the other hand, we can also find, we said this was going to be more extensible, but you know what? It hasn't been. It's actually caused us problems. People have added they've added all these interface hooks. They're not the right way of doing things. It's actually proven to be more complex. We overgeneralized. We made an API that was so complex that nobody knows how to use it. This experience was interesting. I visited a company in West London about 10 years ago that had decided to try and dependency inject everything. It was a .NET project, and because they wanted to make everything extensible and configurable. What it actually turned out when I talked to the team is that there were only 2 people who found it easy to work with. And those are the people who made the decision originally. All the other people on the teams, when you ask them, how do you work with this code? How do you work with this? One of the guys says, I genuinely have no idea what's going on. It's like it's like walking into the middle of chaos every day. He says, I don't understand how the system fits together. And he said, what I do is to make the code work. What I do is I copy and paste something that already works. And then I cross my fingers and then I get it to build. In other words, the architecture had become a maze. It had become a labyrinth. He didn't understand it. It was not more extensible and easier to work with. So, in other words, we have our measurement. It failed. Yeah. In fact, the best book for this, I have it on my desk because I was using it yesterday, referring to it. I'll refer to it later in this talk in a few slides' time. Your Code is a Crime Scene. by Adam Thornhill. Wonderful book about code analytics. The idea is what you do is if somebody says, hey, has this reduced the number of bugs? Well, let's go and look and see where the bugs live. Let's look at the rate of bugs in particular parts of the code base over time. This code makes things easier to change together. Oh, okay, we can look at that. Your version control history is actually a history. It allows you to understand. It's like a doctor looking at the patient of the system and understanding it. So what we've got here is an observation. And importantly, because people have historically tried to divorce architecture from development process, this observation, this lovely book on building architecture by Matthew Frederick, 101 Things I Learned in Architecture School, properly gaining control of the design process tends to feel like one is losing control of the design process. It tends to feel like the opposite. Okay, in other words, there's this kind of paradox. Instead of planning everything in detail, what we have is a more realistic roadmap. And I often talk about the roadmap metaphor. Roadmaps are used by architects, they're used by products people. I think roadmaps are a great idea. The problem is that every time somebody shows me a roadmap, it only ever has one road. And I want you to think about that for a moment and think how useful a roadmap with only one road is. It's not very useful. The whole point of a roadmap is that it shows you more than one way to do something. The whole point is that you show the different options. And as you encounter obstacles, it's like driving with Google Maps in traffic. In fact, I was doing that this morning. One route came up, then another route came up because the traffic was worse in the centre of town. I live in Bristol. The traffic was worse in the centre of Bristol than it was if I took a different route because of new roadworks. The point is, I can't predict the future, but I can show you different paths. If you only show me one path, it means that you are certain of the future. If you have an architecture that relies on one plan for the future and your roadmap only has one road, that is a recipe for failure. You need to have more than one road. That's the idea. That's why properly gaining control of the design process tends to feel like one is losing control of the design process because you're actually showing people options. You might have a favored option, but you're saying, I don't know what all of this is going to lead to. So the observation here, therefore, is prediction is very difficult. The whole quote goes, prediction is very difficult, especially about the future. One of the things I like about this, you'll notice on the screen I put Niels Bohr, Danish quantum physicist, but it's got a question mark. You see, I always thought this was a Niels Bohr quote. My co-authors thought this was a Yogi Berra quote. In fact, if you Google around, you will find that lots of different people, probably even Leonardo da Vinci has been attributed this, and I'm sure somewhere Einstein is said to have said this, and probably Abraham Lincoln said it as well. In other words, it turns out everybody has said this. What I find interesting and ironic about this is we are talking about a quote from the past, and we don't know who said it. If we can't get that right, how on earth are we going to predict the future? Okay, we can't even get our own past right. But that said, the past is more knowable than the future. The past is one of the places that we can actually make reasoned predictions about the future. We look to our experience in the past and we make probabilistic predictions about the future. So, kind of the last thought I want to give you today is this idea of we can't predict the future. How am I going to end up with an architecture? What I'm trying to get across is the idea that many of your decisions will not necessarily be recognized. There are things like architecture decision records that help us fulfill the idea of Tom Gilb's kind of hypothesis-driven approach, the idea that we can go back to things, but there is also the recognition that time is an important component and we can learn more from the past than we currently do. Sometimes when we talk about and complain about our legacy systems, the thing we often forget is that a legacy system has history. And that's a good thing. It means that we can learn from the things that that system has actually experienced rather than the things that we guessed it might experience. So here's a book. This is a lovely book by Stuart Brand, How Buildings Learn. It's actually about building architecture. And there's a couple of points here that I want to make. First of all, the image that you see on the screen. There's an image on the left-hand side, two houses in New Orleans in the middle of the 19th century. And then, nearly 150 years later, the same two houses. What I find fascinating is that if you didn't know that they originally started off as the same design with the same architecture, you wouldn't guess it. They look completely different. They have taken different paths. This should remind us that sometimes when people think architecture, they think, oh, architecture is something in the real world that doesn't change very much. This is entirely wrong. Architecture in the real world changes a lot. It just changes at different time spans. In software, we are used to a rate of change that is far, far faster. In buildings, the changes are sometimes longer than a human lifetime, whereas within software, the changes may live within somebody's work span at a particular company. So they do change. They change a lot. They also last a lot longer. So therefore, their time span is far larger. So if anybody says, "Oh, building architecture because buildings don't change," they need to look at buildings. Buildings do change. They just change slower than we expect. You need to speed that image up like a time lapse image. And then you'll say, oh, yeah, just like in software, things do change a lot. And some changes are more significant than others. The observation that Stuart Brand uses in the book, and he uses this, he talks about it, it was based on the work of the architect Frank Duffy. He talks about buildings having different layers of change. Okay. Now, the message here is don't go out and create 6 layers all beginning with the letter S. You can see each of these layers in a building has a different rate of change. The site of a building, where it is the most stable part of that. The structure, the load-bearing structure, which holds the building up. The skin, the facade of the building. The skin changes faster than the load-bearing structure, changes faster than the location. The services, air conditioning, heating, cabling, electricity. This changes on a 5 to 15 year basis in an office building. The space plan, how things are organized, and then the things inside it, the stuff, the chairs, the tables, these can change on a daily basis. What he's talking about here is that in a functional building like an office building, there are different layers of change. And so it is with software. And we can organize by rate of change. And interesting enough, this pattern can be found in the Big Ball of Mud pattern paper. Shearing layers, different artifacts change at different rates. Therefore, factor your system so that artifacts that change at similar rates are together. It is the idea that we might not be certain of things, but if we understand that we want to move things around, use this idea of code analytics to reorganize things. Do I have things in a higher level, depending on things in a lower level, but the things in the lower level are less stable? That means either the thing in the lower level needs to be moved, it's in the wrong layer, or the thing in the lower level needs to be inverted, in other words, with respect to an interface. Factor out a stable interface and plug in the unstable implementation. So this actually gives us opportunities for refactoring and abstraction we might not otherwise have seen. We restructure the system according to these rates of change. They reflect the kinds of certainty. The more stable something is, the more certain we can be it will behave the same way in future. Things that were stable in the past are more likely to be stable in the future. Things that are less stable in the past are likely to be less stable in the future. And this is where I refer to Adam Thornhill. So if you weren't sure about that reference, here it is. He also talks about this measuring change frequencies is based on the idea that code that has changed in the past is likely to change again. It's not a perfect prediction, but it is a probabilistic forecast. The other way that we can deal with things that we don't know is to use knowledge. Again, this is very old advice. This is 50 years old now. Parnas's advice on how to modularize a system. We can't be certain of everything, but sometimes we know when we're uncertain. Okay, this advice is really simple. We propose one begins with a list of difficult design decisions or design decisions which are likely to change. Each module is then designed to hide such a decision from the others. And this is interesting. I've done this with groups where we kind of sketched out how to kind of build a system, which from the class level to the API level, whatever we're talking about. And it's just like, you can hear it in the room. When somebody says, oh, we're not sure how we're going to do that, that means that's a decision that is likely to change because we don't know how to do it. Or when two people say, oh, I was thinking we'd do it like this, and another person says, I think we should do it like this, that's a decision that is likely to change. Instead of thinking I need to do it one way or the other, the fact that people are not sure and do not have knowledge in advance is a warning to you. It's an indication. Oh, look, this knowledge is unstable. Therefore, we should insulate it and modularize it, put it behind an interface. So in other words, we can use our lack of knowledge and our uncertainty as a structuring mechanism. So I will close on that observation from Voltaire. Uncertainty is an uncomfortable position. Humans find it immensely uncomfortable. but certainty is an absurd one. And I want to get this idea, the very fact that you are not sure of something is itself interesting, and you can use that to help structure a system. The fact that something keeps changing in a particular way tells you about what it is likely to do in the future. You might not be certain about what it's going to change to, but you are more certain that it will change, rather than having a false certainty about that. When two people talk about something and can't agree, the challenge is not to agree, which is what we normally think it is. The interesting thing is the fact they don't agree. How can I design so that their disagreement becomes encapsulated? In other words, I don't organize by abstraction. This is the contentious bit. And what I did with one team is we actually structured a system based on people's uncertainty. Rather than structuring it in terms of classic abstraction techniques, we sort of thought, how sure about this? If everybody's agreed on it, let's say it's certain, or more certain than anything else. If people can't agree on it or they don't even know, let's isolate it, let's insulate it, let's separate it.